Okay, welcome to lesson 28, checkpoint, question 10. What two-dimensional cross-sections could be created by slicing a square-based pyramid? Select all that apply. Okay, and I found a help set that has it set up that you can look at cross-sections and solids. So I'm going to look for a square-based pyramid. Which is right here. And if you notice right now, the cross section I'm taking would be a square, and this would be parallel to its base. So we could have a square. If we took the cross section, that would be parallel to its base. We can also find I'm going to go to the rectangular pyramids really fast because it has a better example. We could, if a square is a rectangle, so all of the base would be the same, but if you notice right here, we could create a trapezoid by connecting the opposite sides in our base as we move up and down. So we could make larger or smaller trapezoids. So we could have a trapezoid. And if this was completely vertical, we could also have our trapezoid as well. And we could cut it as a triangle. So there we have a triangle cross section. So we could create a trapezoid, a square, or a triangle. And then question 9, identify the three-dimensional figures that could have a square cross-section. Well, one of them was a square-based pyramid. One of them is a cube, since a cube is a square, any cross-section of that would be a square. The other option would be a sphere. We can eliminate a sphere right now because they're all circles. So this one, a triangular pyramid, we rotated it. We could create a trapezoid, but not a square, since these two top points would be closer together than the base points. So a cylinder, if the cylinder had, we cut it this way, and right here you can see we could create a square if our diameter was the same length as our height. So we could have it from a cylinder. And a rectangular prism, we could have a square from a rectangular prism. If we connected at midpoints, so we could have a square right there at angles to a certain point down the length of a side. We could create a square there. So we have a rectangular prism. And which of the following shapes could be sliced to create a pentagonal cross section? A cube, a sphere, a square-based prism, a cone, a triangular prism, or a cylinder. So I know in the example it had a cube, so if I move this right there, we could see, we can count that there's 1, 2, 3, 4, 5 sides to that cross section. So a cube, a sphere doesn't have any hard edges, so we couldn't create a pentagon from that. A square-based prism, I don't know what I clicked on. We could also create it. It's the same scenario. If this height right here was the same, I could cut it the same. If the height was the same as its length and width, I could still make this similar cut. I want to say it's like that. Nope. One, two, 3, 4, 5, 6, 7. Was that? It's if we cut off a corner. So if we were to cut off a corner of our there we go. 1, 2, 3, 4, 5. If we're cutting off a corner of our prism, so a square-based prism would be similar to the rectangular prism, except for all of the sides would be the same. A cone doesn't have enough flat surfaces to go through to make a pentagon. A triangular prism would work. There are 5 faces to a triangular prism, so if we were able to cut through all 5 of those sides, then we would be able to create a pentagon. So if we're cutting through all of the sides, 1, 2, 3, 4, 5, there's our pentagon. And a cylinder doesn't have enough hard sides or flat surface sides to create a pentagon. So if the shape has 5 or more flat surfaces or surface faces, then you could create a pentagonal cross section in it. Okay, what two-dimensional cross sections could be created by slicing a sphere? So if we were to look at our spheres, this one is going up and down, so we would have a circle or a point. If we rotated it vertically, we could have a circle. So, circle only. Okay, question 6. Describe the three-dimensional figure obtained from rotating the following figure around the y-axis. So they want us to spin it around this axis, and the resulting three-dimensional figure will be a blank with a radius of blank units. So we can count the radius right now. So 1, 2, 3, 4 from the center point to the out, and when you spin something, it's going to create a circular base. It's going to keep that radius length the same, so we're creating a circular base, and therefore it will be a cone since it's circular on the bottom and it comes to a point with a radius of 4 units. Okay, describe the three-dimensional figure obtained from rotating the following figure around the y-axis. So we have a triangle, and it's rotating around the y-axis, and any point that's rotated around a fixed point will follow in a circle. That's what our radius is, so it'll be a cone again. And it'll have a radius length of 3 units. Before we go on to question 4, I'm going to give you your tip, which is, you may already do this, but if you take your fingers and you pinch right here in between the webbing, you're hitting an acupressure point, and it will help you relieve stress or anxiety. And just take it, I do it just a few times on one side and then a few times on the other side and a few times on the other side. So if I'm reading a question, I'm holding my hands in my lap and I'm pinching in between my thumb and my pointer finger right here to help me stay calm so that my brain can receive the oxygen and think clearly for my questions. So this one is called the Union Valley, right here in between the webbing of your thumb and pointer finger. That's another acupressure point to help just quickly relieve some tension. So question 4, describe the three-dimensional figure obtained from rotating the following figure on the axis. Since we have a rectangular surface here and we will be rotating it, if we are rotating around a point, well, rotating a point, we're creating a circular arc path. So we're going to have a circular base with a height, and we're going to have a cylinder. And the radius will be 1 unit, so it's from its center to the corner that will be rotated. So question 3, describe the three-dimensional figure obtained from rotating the following figure. We've rotated a triangle again. This will create a circular path around here as we rotate it. So the base will be a circle. If I rotated it all the way around, the base would be a circle, and we would have come to a peak right here. And so we will have a cone with a radius length of 1. What two-dimensional cross-sections could be created by slicing a triangular prism? So we go back to our triangular prism. Right now we have a cross-section of a triangle. So we could have a triangle because we can slice through parallel to our base shape of a triangle. We could also have a rectangle if we cut parallel to the very bottom. It could be possible to have a square if and right now I'm seeing a pentagon again. So 1, 2, 3, 4, 5, which isn't an option. Trapezoid. Let's see right there. So if we connected 2 points at the top of the triangle with 2 points near the base, we can create a trapezoid. A hexagon has 6 sides. Triangular prism only has 5 base surfaces, so I could not create a hexagon. I could create a square if the length right here on our base was the same as this length. So it could be possible. I'm just messing around to see if I can grab a picture of it for you. So, it could be possible if you had constraints on the length of your triangular prism. And I don't know if they're considering that, so I'll check the answers. Consider the following three-dimensional figure. Which of the following figures is a cross-section created by the plane cutting through the cone? Well, if I look at the plane, it has a circle in there, so it's a circle, and I want to check to make sure that to see if they're considering the constraints that you could place on the length and width of a triangular prism. So let's see. Alright, so this one I would say that the square was not the option. So they're not considering those. And there you have it.